Okay, well, good morning, class. Good to have you all today. All right, hope those of us here had a good spring break, and those in Michigan, I guess you were bored. Okay, well, I guess doing other class stuff and working on your projects. So it was fine. It was good. I'm running out of adjectives other than it was good. How was your break, Cameron?
Pretty good. We're done again.
Then Tampa. I went up to North Carolina. That's where I went. So great. So today, we're going to continue talking about model predictive control. Okay. And I'm going to try, and I'm going to, we're down one TA today who's normally keeping an eye on stuff. I'll do my best to keep an eye on the chat. Okay. All right. All right. We're going to MPC implementation. Continued. Now, my apologies that the lecture video is not up from last Thursday. I'll get that remedied soon. There was an audio issue, but it's one that could be fixed. But the code that we covered in last class is now up. Okay, so you can go if you are on your computers now, you want to download the code to continue working on that. That code is up on the files page on Canvas. So, okay. So recall, we were using model predictive control MPC for a double integrator. In 2 dimensions. So we had this hockey puck, which I will counterintuitively draw as a square. And we had some force in the y direction, force in the x direction. This is xy. It's got a mass. And we want to use model predictive control to control it, maybe send it to some desired position. Here's some x desired and some y desired over there. Okay. Want to set it there. Now, smarty pantses among you, I'm sure it could whip together a PD controller to do that, not a big deal. But we want to do it with optimal control. We want to minimize some integral from 0 to some capital T of some quadratic objective. Okay. So Q transpose capital Q, Q plus U transpose capital R, U. I forgot to ask my Michigan friends, how are we doing today? Doing all right? Doing okay? Thank you, some of you for the feedback at the end of the last lecture. It's cool to have you. All right. So dt, and that's our cost function. And we also had constraints on our control inputs being less than minus f max, sorry, greater than minus f max and less than f max. Okay. They wanted to use model predictive control for this problem. So just as a reminder, okay. Now in MPC, what you do, the first thing you do is you sample the current state. Could we close that slightly? Thank you. Thank you so much, Ash. Sample the current state Q. 2, you're going to set up and you're going to solve a trajectory optimization, solve a trajectory optimization problem. So you're going to formulate and solve a trajectory optimization problem. And that problem is a finite horizon. Capital T, okay? That's that capital T, it's right up at the top, right there. All right? And 3. So what you should get out of that trajectory optimization is some optimal set of control inputs and states, right? Yeah. So you want to apply the optimal control inputs for some small sampling time call it TS. Oh, blocking the feet. Better door than a window. Okay, all right. TS. All right. So imagine you had your control inputs over time, your optimal ones, call it U star of T. Those are our best inputs. All right. Over time. And it came back as some set of control inputs. These are your best ones. That's your capital T. That's your time horizon. And TS will be some shorter period of time. Say it's that. That's TS, right? So you're likely not playing out the whole trajectory of inputs, just the beginning, right? Okay. Then you go to 1. You sample that state. Again, rinse and repeat. MPC. I'll zoom out for you folks. Okay, and what we were doing last time is we were focusing on step number 2, which is probably the most complex step. We just dove right in, which was a trajectory optimization problem. We've done this before. We've done direct collocation, right? And this was a direct collocation problem. Now, are we setting up a particular kind of mathematical program? Gesundheit's correct. Anyone else could be right. Quadratic program, right? And particularly a convex quadratic program, right? Now, what allowed that to be a quadratic program? Can any trajectory optimization be a quadratic program? No. No. What about it made it that for us? What about it? Yes. Quadratic cost function. That's one key component of it. Exactly. What's another one? Anything about the dynamics? Could it be any old dynamics? Linear dynamics. Yeah. Yeah. Kevin Superb said linear dynamics. That's right. Thank you. Yes. Thank you. Cool. So FYI, the students can see what you type. So cool. All right. Exactly. So linear dynamics, quadratic cost, linear dynamics. This is what gives us this problem. Okay. So now that I just want to point out, because we kind of leapt right into the trajectory optimization phase of that last time. We spent a lot of time setting up that problem. Okay. And what I hope to convince you is that that's most of the task. Okay. And we got almost all the way through the trajectory optimization setup last time, almost all the way. Then we went on spring break. So, okay, so let's go back to our code. So if now it would be a fine time for us to go flash back to the code. If you got your laptops in front of you, that's all cool. And let me just end my share screen here. Okay, whoa. Okay, we're good. Sorry, just indulging. So I got up here my MATLAB code, and I'll share it with everybody. Oh my goodness, my MATLAB froze. That's never happened in the history of mankind. I had it up ready for you. So as I reopen MATLAB, just quit out here, force quit. So one thing we did a lot more this time is we generalized our dynamics as being Q dot is equal to AQ plus BU. And that allowed us to set up our defect constraints in a pretty formulaic way. And I'll walk through what we went through. Oh no, Times font's not available. How will we live? Okay. Let's make this larger. Font. 30. There you go. People see that reasonably okay? I know that the folks in Michigan can't see it yet. Now they can. Glorious. We're all good. So we had two functions, one of which was our main script, okay? And all it's doing right now is running a trajectory optimization. It's running the trajectory optimization that it's given, okay? And the other function, the other script was something I call gen functions, okay? And this is doing the process of coming up with all of the information a quadratic program needs. What does a quadratic program need to know? Anybody? It needs to know that, well, it doesn't know anything about dynamics. It knows cost functions and constraints. Where are the dynamics though? Which of those two things? Yeah. In the constraints, exactly. Yes. So so we have to give the quadratic program the cost function and the constraints. Okay, and we give that to our cost function in the form of this H matrix, which is our Hessian. This C matrix, which was the C vector, which is the gradient of our cost, and these A and B matrices. Okay, if we have those matrices and vectors, we find our quadratic program. Sounds easy enough, right? What we dove into last time was setting that all up in a really general way, or a pretty darn general way. I'm sure you all can do better, okay? Even more general if you want to, all right? Where we set up a symbolic set of states, a symbolic state vector. Is ringing a bell for some folks, okay? I know it was before, it was over a week ago, so. And we set up our control input vector of u's. In fact, you can run our gen functions and you can see what each of these things are, well, really quickly. All right, it's almost done. Anytime. It's generating all the functions right now, but I just want to show you what each of these commands has done. There we go. Oh, it's still running here. So it sets up a state vector, control input vector. And this A and B matrix, they are not the A and B matrix for the quadratic program. What is that A and B matrix? What is that for? For the dynamics. It's x dot is equal to AX plus AQ plus BU. As you can see right now, right there. Those are our dynamics. Okay. So that sets up our dynamics here. As it says helpfully there, dynamics. All right. Then once we have defined our dynamics, we also need to know what all of our decision variables are. Okay. So we're using direct collocation. So we need to have decision variables for what? control input. And what else? The states. Okay. Define symbolic variables for each state at each node and each input. Okay. So our system has how many states here? Four. Okay, it's a double integrator in 2 dimensions. So it's got 2 second-order differential equations. It's going to end up with 4 states. So we use this setup here to give us our first-order dynamics at every node. Oh, my goodness. We have A times Q plus B times U. So if I looked at what DQN is, let's say DQN, prepare yourself. Okay, here we go. Okay. You can see we have, these are the dynamics of each node. So it's saying that the dynamics of the first node, basically the first derivative of the first state at the first node is equal to the second state at the first node, meaning that the derivative of position is velocity. And it does all that for us. And the convenient thing is if we wanted to add in different dynamics, right now this is just a sliding mass with no friction. I could add on friction. Okay, I could do that by adding on a -1 here and a -1 here, just because I've done this a few times. Okay, and it'll regenerate all the dynamics with sliding viscous linear friction. Okay, that's why I've set it up this way. Okay, I'm gonna cancel out of this here. Okay. And we then define our finite time horizon, T. We have dt, which is the time between the nodes. Okay. And we use this all to set up our defect constraint. All right. And I'll skim through some of this, but what we ended up doing is defining our cost function, which this is that cost function I put on the board before. The only difference is it subtracts our Q desired minus our Q actual. Okay. All right. So we generated all those. We generated all those functions. Okay. And what happens at the end of our gen function script? What does these MATLAB function commands do? What do they do? What do they do? All right, I know. They export MATLAB functions. There they are. Boom, 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 boom. And if folks are popping in the chat, I might not be able to see it. So let's see. Just FYI, put that over there. Okay, great. All right. So whenever you run this gen functions command, it created all these functions, one called hfunc, that's our Hessian. And if we open it up, eventually it'll show me. What's inside that? Okay. Eventually, I'll just leave that be for a bit. It'll eventually show me. Okay. But basically, I've created all these functions that main can call. So all our main function is right now, we're running a test optimization. We're doing the run a trajectory optimization part of the course, or part of the process. It grabs what H, C, A, B are, all those things. Okay. And it runs quadratic program. You run that. Okay, apparently I must have aborted the command is probably what happened. Give me a second here. I'm going to fix this. Run that real fast. So I ran a trajectory optimization. Boom, minimum found that satisfies the constraints. How about that? Okay. And it gave me X star. What is X star here? That's the command. Optimal decision vector. Exactly. Exactly. Okay. the optimal decision vector. So what do all these mean? Well, that's a great question. I'm glad you asked. Okay. What are all those decision variables? Well, if you need to know, you can go and take a look at how we define our decision variables in our gen functions command. Here's our decision vector, X. I use this approach to building my decision vector. I use those commands. All right. What does that actually look like? Well, I'll run it and we can actually look and see. So I'm going to run X. You can see, the first one is the first control input at node 1, the second control input at node 1, the first control input at node 2, et cetera, et cetera, et cetera. Okay, until you get all the way up to your first state at node 1, your second state at node 1, and so on. So if I wanted to know what all of my control inputs are, I would need, for the X direction, I would say this one, this one, this one, this one, and this one. Okay. That'll give me all of my control inputs over time that I would need to apply those control inputs. So I'm going to then, let's plot it. So I'm going to plot X star. I'm going to need the first one. I'm going to need every other one until 2 times the number of nodes. The number of nodes I chose was 5. Let's run that. Yes, that's what I meant. Thank you. Okay. There are my control inputs. It looks like it's 1, 2, 3, 4, 5. Yep. So basically, it looks like it went all the way on, all the way down, back up. Okay. Want to see whatever the other control input is? We would start with the number with the second index. Skip over 2, skip over 2, skip over 2. Close all. Same answer. Looks like it's decided to drive it both to both places the same way. Okay. That's just one trajectory optimization that it ran. Notice it's for 5 nodes. Okay. All right. I'm going to change the number of nodes so we can see a bit more of a clear trajectory optimization here. So I'm going to say in my gen functions command, if I want to change the number of nodes, I change n and then I rerun it. And we wait for a second. Okay. I see not everyone has a computer, so it's not always the most riveting thing for people to watch. Okay. Are you able to download the code at all? Okay. All right. So you got that running. Notice when you add more nodes, it takes longer to generate all these functions. That's the symbolic toolbox doing its work. Right. And if you were to use and this thing that we made, this code that we made for gen functions, if you grab any trajectory optimization package online, things like Casati or Frost or things like that exist, you can Google online for trajectory optimization packages. They almost always have a stage of the code where it does exactly this, where it generates these functions. Okay, we ran that. I ran the trajectory optimization. Trajectory optimization went really fast. Oh my God, look at X star. I'm still scrolling. You have how many decision variables? NumL X star. 126 decision variables. Okay. Solve that pretty darn quick, right? How long did it take to solve? Tick, tock. 0.02 seconds. That's pretty slow, honestly. Can we go faster? There we go. We run it a few times, it actually does better. So my laptop, there you go, 5 milliseconds. I'm cherry picking the best one. Okay. Right. So now let's actually plot X star. Let's plot our control inputs over time. So X star 1 colon 2 colon 21 times 2. Here we go. Looks like we have all the way on, all the way off, all the way on. Okay, or say 10 minus 10, 10. It's clearly trying to rail the control inputs here, is what it's trying to do. Okay, what about for the second control input? Same deal. Okay, why is it trying to do that? Well, you'll notice in my main function, I defined a Q desired. See that? So that first state, that's my X position. This second state is my Y position. And my initial state is 0, 0, 0, 0. Now, what happens if I make my desired Y position 0? This is a good check to do when you're doing your optimizations, a good sanity check. Hopefully, it should not be applying a lot of force in the Y direction, we hope. I didn't screw something up. So I ran it, ran the optimization, having changed the desired Y position. Oh, thank goodness. This is my Y control input. It's all zeros. Okay. All right. So now it chose to do that, interestingly, okay, in part because look at my Q vector, my Q matrix. Now, the Q matrix assigns a penalty to what in the cost function, the state or the control input? The state. That's right. So the bigger I make this penalty, the more it's going to try to penalize state error. Okay. R is the opposite. It's the control input. So right now it's railing against the limits I set, plus or minus 10. Okay. Well, if we try to make it more efficient, I can instead make this 1 times the identity matrix and maybe make this, I don't know, 100 times the identity matrix and give that a shot. So I'm going to run that. I'm going to plot my first control input. Yeah, still going, still like in a rail. See if I can get it to go. It's still like in a rail. Makes me feel like I've done something wrong here. Let's see. 1, 2, 21 times 2. All the way on, all the way on, all the way on. Q desired R. Okay. We'll move ahead for now until we fix this issue, but it can run a trajectory optimization. Clearly, it's trying to try to push its way toward the goal. So if it needs to move to the right, this is our control input to the right. It's all the way on. Clearly must overshoot or something, then undershoot. Okay. So let's assume for a moment we've done a proper trajectory optimization. Okay. A bold assumption, but for the purposes of class, we'll go with this for now. So that means in our process, we've done step 2. What's step 1? Sample the current state, then run a trajectory optimization, then use that trajectory optimization, use that control input for a certain period of time, right? So let's do our actual MPC loop, okay? And for that, we're going to need a few things. Number 1, we're going to need a simulation of our system to actually run, okay? So let's go and add a simulation. So I'm going to create a simulation, which means I'm going to need some ODE function, right? Okay. So ODE, so I'm going to make a function. Our ODE function returns the derivatives of our states, dq, which is equal to ODE fun. And it's going to take in, what does our ODE function need to take in general? You've done this a few times for your homeworks. You mutter slightly louder. T and Q, time and state, right? Okay. And we're also going to need, so at a minimum, we need those things. We're also going to need our control inputs, right? Okay. We're going to need to know that in order to apply our control. So I'm going to give it U as well. Okay. All right. Now, thankfully, we already have our dynamics are pretty simple. It's dq is equal to A times Q plus BU, assuming that we define A and B. Let's just grab A and B from gen functions. It's going to steal it. We defined it there. There's probably more efficient ways to do it. Okay, where you can there you go. That's our dynamics. Not bad. Takes in a state, takes in an input, gives me a derivative of the states. That's all you need, right? So that's what you need for your ODE function. Here's a trick for you folks. You notice how it's highlighted there? That T, see that? Why is that highlighted? Well, it tells me you probably can't see it in 0-point font. Input argument T might not be used. It's just a silly, like it's a silly little warning in MATLAB saying, hey, it's inefficient code. If you don't need to use something, it's entirely optional. Put in a little tilde and get rid of that warning. Okay. There we go. ODE function. All right. So now I'm going to create a new script. I'm going to call it run mpc.m. And this script's job is going to run our MPC controller. Okay. It needs to 1, sample the current state. 2, run a trajectory optimization. And 3, use the optimal control input for TS seconds. Okay. Have I beaten that in your head enough? Non-violently? Metaphorically? Okay. All right. We're going to CLC. We're going to clear. We're going to close all. Okay. I'm going to have an initial state. Q 0. 0, 0, 0, 0, 0, 0, 0. Okay. I'm going to have a Q desired, just like I have in my other code. I'll make it 1, 0, 0, 0. Okay. We can change that later. In fact, I'm going to go and copy a lot of my stuff from my main command, just because I don't want to destroy this beautiful main command I've already written. I'll just copy it over. Okay. I'm going to copy everything. I'll even including the T equals 1. Boom. Okay. I copied that all over. So basically it's the same thing as main. And you can see here that we have defined our H function, our R, Q desired, all that business there. Okay. All right. I think I might see where an error might be. We'll get that in a second. We'll get the structure in here. So we've defined all of our parameters. Define our parameters. Here's a quiz. What is T? Capital T? I'm sorry. Again, my ears are going. Finite time horizon. Thank you. Here's our initial state. Here is our desired state. Here is our, we'll call this the state cost. Okay, the Q matrix. Okay. And R matrix, that's the input cost. Okay. And here's our maximum force. Okay. All right. Now we're going to do our simulation and MPC control loop. Okay. Let's do a quick simulation test. We've defined our ODE function, but we put in an extra parameter. So we have to use a trick to send in an extra parameter, right? Okay. So that means we need to define an anonymous function. We'll call it ODE fun param is equal to at T comma Q, and it runs ODE function with T, Q, and U, not U import. Okay. And we'll define U, our control inputs, as 0, 0. Okay. So that means I can run ODE 4.5. I can run my simulation now. I have everything I needed defined. So T out, Q out is equal to ODE 4.5. We're going to send in our ODE function, which is called ODE fun param. Send in our time span at 0 to 10 seconds. Why not? And our initial state. Well, just make it Q0. Okay. All right. I'm just going to run all that. And I'm just going to plot, just make sure that everything doesn't move. Right now, there's no control input. So if I say, hey, plot T out, Q out, colon, comma 1, this should be the X position, the horizontal position over time, doesn't move. Great. I'm going to rerun it with a force on the X-axis. This thing should hopefully accelerate. I'm going to rerun my plotting. There you go. That works. Okay, that's working fine. It works. Okay. Comment this out. Copy. So what we need to do, we're running MPC. We want to do that 3-step process, right? So we're going to do it in that process. Okay. So it's going to be in a loop. So let's make a loop. All right. So how long is that loop going to run for? Well, we'll define it. We'll say it's 10 seconds. We'll call it T final. It's equal to 10 seconds. We need to find a sampling time, right? TS. Let's make it 0.1 seconds. All right. So we'll create a little simulation vector of numbers of times we want to run this, being equal to 0 to TS through T final. Okay. And we'll do a for loop. For iter is equal to 1 colon number of elements in tsim. That's how many times we're going to run this loop. Okay. Now, step 1. Sample the current state. Well, we have the current state already defined. It's called Q0, right? So it's all the way at the top right there, right? So say, so right now it's Q0. You'll see we're actually going to do this at the end of the loop. Okay, so we know that Q0, that works. Okay, now step 2, formulate and run the trajectory optimization. Well, we've already done this. Okay. We're going to, all we need to do is define our matrices that are dependent on B, A, Q, etc. Okay. Done. Now I'm just going to put some semicolons behind these so they don't yell at me constantly in the command window. All right. That's step 2. We spent all that time doing step 2. Now we have it. Now step 3. Run, or so we want to apply the control inputs. For TS seconds and apply the optimal control inputs. Okay. So it's helpful to know what those are. Well, how do we get those out? Well, if we know the number of nodes, which I have inelegantly just said is 21, okay, that means that U1, our first control input vector, is equal to X star 1:2:21 times 2, because it was every other variable, right? Starting with the first one. Well, what's U2, which is this is our horizontal force. U2 is our vertical force. That's X star. It's every other control input starting with the second element. So 2:2 n times 2. That's your vertical force. And these are over time, right? These are for all the different nodes. I'm going to put the end statement there. What I'm going to do is I'm going to put just to show what's happening here, I'm going to put a break in the code. Now in MATLAB, you can, I think, put a little thing there. You can click on the side. That's fine. I like to use the command called keyboard. It's a good debugging command. It does the same thing. So what it's going to do is when it gets that line of the code, it's going to stop running the code, but I can go into the command window and start typing stuff, see what's going wrong, if anything's going wrong. So I'm going to run that. Boom. I ran it and look, oh, it says helpfully, look, Christian, you just stopped right there. Very cool, neat, nifty, neato. It ran the trajectory optimization, came up with U1 and U2. And because I stopped the code, I can do whatever I want right now. Right now, U1 has a bunch of variables in it. Looks like it's a 21:1 double. U2 is a 21:1 double. Little floating point numbers. So I'm just going to plot U1. There we go. It does the thing where it goes boom, 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 boom. Not sure that's right, but it's a thing. Okay. We're going to apply that thing. All right. And if you're done, if you're like, you ever get confused, I can't get out of keyboard command. DB quit is debug quit. Okay. Get out. Seems to be working fine. I'm going to get rid of my keyboard command. So now I need to apply my control input for my control input for how long? TS seconds, right? So now that means I'm going to simulate my system with the control input for TS seconds. So I'm going to make my ODE fun params as my anonymous function. Needs to take in time and state. Okay. And it's going to run ODE function, which I've defined as taking in time, state, and control input. Was that people? That's you. I'm sure that's what you said, and that's right. Control input. Okay. All right. So time, state, and control input, and it's in a vector. So it's the way I've defined it. Okay, so what control input do I apply? Well, I have my set of points defining my control input over time. I can interpolate along those along those points. So if I look at my handy dandy plot, which went away, or did the plot go away? Run the plot here. Here you go. And I'll give this a handy dandy X's. Here you can see the points that came out. I know it's really tiny. I'll make it slightly bigger. You see the X's though, right? See, it's high, 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 0, low, 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 low. All right. And if you're at, say, this time right here, let's say it's 1.5 seconds, you can interpolate between these 2 points, right? This is a reminder what what interpolation does. So for that, I use the interp1 command because I'm interpolating along one dimension, just along one line. That's what it means. Okay. So I need to give it a series of time points. Okay. And that's going to be lin space between 0, our time horizon, and n. Those are my time points, right? Just from 0 to 1, which is my time horizon, with 21 points in the middle. Okay. Those are my time points. What are my vertical points or my control inputs? It's U1. Okay. And what time do I interpolate at? What time am I interested in? Or whatever time it is. T. Boom. T. Okay. Now that's for U1. Now we want to do U2. So we're going to put it using a semicolon just below. So it's now U2. Interp1. Okay. Now we just need to change this to U2. So now we've created a new ODE function that runs our dynamics, but it also interpolates what control input we need. Do I need to say that louder, or is that louder is clearer, right? Okay, it's more obvious. Okay, all right. We set that up, so now we can simulate for a short period of time our dynamics with these controllers. So we're going to say T out, Q out is equal to ODE 45. That's our simulator. I'm going to give it ODE fun params. How fun. And we're going to run it for how long, Ash? You gave me the right answer before. That's why I'm TS. Thank you. Yeah, you did it. You did. We're going to run it for TS seconds from 0 to TS. Okay. And we're going to use it at the current state, which is Q0. Okay. All right. And there you go. Okay. Now, as a debugging measure, it's a good time to stop and make sure things are working. Okay. If I were at home and I was doing this, I would go back and check the trajectory optimization more, but I'm going to check this right now. So what I'm going to do is I'm going to do a debug plot, where I'm going to just plot T out and just the horizontal input, okay, in the horizontal state, okay. So it's going to just that's the horizontal position, okay, over time. And I'm going to pause it. Now, you might recall step 1 was sample the current state, which we cheated and said, we know what it is, but now we need to update it. Okay. We're going to say, now sample the current state. That means that Q0 is going to be the last state of our simulation. Okay. The last state of our simulation is going to be the last row that ODE 45 gives us. We want to turn that into a column, so we're going to transpose it. So Q out, end, comma, colon, last row, every column, and do a transpose. Okay. Now, if I run this, what should happen is it should sample, it should run a trajectory optimization, play that use that control input for a little bit of time, sample the state, repeat. But I put a little pause command for this little plot. Okay, let's see what happens. All right. Okay. Here's my horizontal position. You see, oh, look, we're starting to accelerate. Okay. Let's go a little further. Okay. Still going? Still going? Still going? Still going? Oh, we overshot. I see that's a number 1. I'm trying to go to number 1. See that? Okay. Oh, I overshot. No, please come back. Okay, going. Oh, or I undershot. Look at that. Oh my God. It's actually working, folks. Okay, that's what I'm trying to say. I know it's hard to tell here. Okay. It's just playing the simulation for each of the little times. Oh, look how close we are. Gorgeous. Beautiful. Okay. Look at that. Sorry, I'm happy. There's probably some small things to fix, but well, it's just kind of zipping around. Look how close it is. 0.99999. I'm close enough. Okay. Now, let's actually have it plot the whole simulation. All right. Instead of me clicking through these little bits of time. Did that make some sense what you saw? What's happening? Okay. I don't know. It's like a movie. I don't know if Hollywood would pick it up, but you know, I do have some contacts out there, so who knows? So, all right. So now let's actually pull. So I'm going to exit out. So how do I exit out? All right, I'll tell you what. There we go. We're done. All right. Okay. So we have it. So now get rid of this debug plot. All we need to do is store all these time points and all the states for all these simulations. Just store them all in a big matrix. Okay. So I'm going to create a, call it T all, make it an open, close, just vector, and Q all. There are probably better ways to do this technically. Okay. But all states and all time. Okay. And what we're going to say at the end here, that once you've run a simulation, you say that, oh, T all is equal to T all, and you pop onto the bottom, T out. Okay. Now we're almost done. This is almost right. Okay. The only issue is that we are simulating time from 0 to TS, right? So we don't want it to be 0 to TS, 0 to TS, 0 to TS. So we're going to have to add a number to how far we've come at the end of TS. Okay. So what you want to do is you want to say T out plus, well, what was the current time we're starting at? Well, we can look that up. It's in TSIM. It's stored in TSIM. Okay. So you would say plus TSIM iter. So whatever iteration we're on the first iteration. Our initial time is going to be 0. We have nothing to add. Okay. And Q out. Sorry. So we want Q all is going to be equal to Q all and Q out. Okay. And once that's all done, should be able to plot T all, and we'll plot Q all colon comma 1. So this is going to be plot the horizontal position. There we go. It is tracking to the horizontal position of 1, which is what we said. Pretty cool, right? Yay. Okay. Now let's try messing with some stuff. This will be fun. Okay. So one, we can also change, just to make sure everything makes sense. We can change our desired position to 2. Cool. See what happens. Hey, it went to 2. Like we know what we're doing or something. Okay. Hey, we don't have to go to just a position. What if, my friends? What if I just wanted to go to a particular speed? You seem intrigued by that notion. Yeah. Okay. Well, let's do that. Let's change it to let's make it go to a 1 meter per second. I don't care what the position is. We'll see what happens. I haven't tried this yet. Who knows? Well, it didn't like that. I wonder if I gave it a wrong thing. Oh, well. There might be some kind of error in there. It goes the right position. What happens to the other thing? All right. Oh, you know what? Oh, okay. No. I know what's going on. I know exactly what's happening. I'm a silly goose is the technical term. Okay. I've done this before and I made the same mistake. Okay. If I wanted to go to a particular position, to a particular velocity, right, of 1, it's still trying to go to a particular position as well. It's like, you know, DJ, I want you to stay where you are, but also walk at 1 meter per second that way. You can't do both. It's compromising. It tries to compromise. All right. So, all right. That's what's happening there. So we can now tell it to go to different positions, and that's neat. And if we want to make sure it goes to both the horizontal and vertical positions, we can do a subplot. Subplot. Who needs a refresher on the subplot command? Anybody? No one's willing to admit it? Okay. It's a 2x1 subplot. We want the first plot. Do X label time. Y label. X position. And then I'm going to want this all for second subplot. So it's a 2x1 subplot, 2 columns, 2 rows, 1 column, second one. And I want my third state. Boom. Okay. And that's my Y position. There we go. They both go to 0, which is, I think, what I asked it to do. If I want it to go to, this is the fun part, folks. So let's make good. Let's have fun with it. Have it go to 2. And Ash, what's your favorite number? There we go. Okay, 2 and 7. All right. So that part seems to work okay. Okay. Let's see if we get any differences. A good way to debug is that, hey, if I want to care more about efficiency, maybe it'll slow down the convergence. So if I want to care about efficiency, what should I make bigger, the Q matrix or the R matrix? What's that? The Q matrix, if you make it bigger, will make it converge faster. Okay. If you want to use, if you make the R matrix bigger, it will want to use less control input. Okay. So make the R matrix bigger. I think that might have taken longer, might have overshot less. Let's take a look here. Let's give a 100. Hard to tell at this stage. Okay. I love it. Okay. All right. Second here. Give me a second. Let's see if it's doing any difference here. No. I think there's some kind of issue. I'll have to debug in the code offline, and we'll do it in front of your eyes. But you can see it's clearly tracking the point. All right. So what are things that you can change about this controller? You can change the Q matrix, the R matrix. You can also change the time horizon. You'll notice that when my time horizon is really short, okay, and I'll just change my Q and R matrices just back to identity matrices. Okay, 1 second, I guess is reasonably short. You can see how it's probably railing the control inputs more. But if I give it more time to think ahead, it'll plan out its trajectory a little bit more. Okay. Yes, question.
So if you did want to just have a desired velocity, would you throw a 0 into that Q matrix?
No, the 0. Oh, yes. Yes. That's a good way to put it. So let's try that. I won't guarantee it will work. We don't want to put in an actual 0, I would say. I think whether it needs to be positive semi-definite or positive definite. If it needs to be positive definite, it might need to be slightly above 0, but we'll try it. Okay. So let's go back to 1. I think there is some kind of glitch in my code, so that also be what's happening here. So if you wanted to change your Q matrix to be Q, we don't care about the positions at all. So we'll make it 0.001. I think there could be an issue with this, which is why it's happening. Oh, I know what to do. We say Q11 is equal to 1e minus 4. And we say Q33 if I wanted to make the Q matrix not care about the position, which entries should I make near 0? Yeah, it's what I had. I was trying to hide it. Okay, I'm sorry. I realized that was a good quiz question for you. But, the first entry, the upper left would be for the first state. Down diagonally, that's the second state. Third, the third state. So the first and third state would be these. Okay. And let me try a Q desired of 1. We'll see what happens. See if it actually does anything like this. Now I think it's oh, actually, this is interesting. Notice how this is super cool. Look at that constant velocity it's coming up with right there for a while until it gets really close. Okay. I can't say we solved the problem, DJ, but there it seems to come up with it looks like a constant velocity. And I think that because there's nothing stopping it from accelerating faster. If I were to change the velocity to be faster, would that make it a little better? Yeah. Oh, look here, it actually cares about going faster. So it's an interesting game you can play with Q's and the R's and the desired thing. Okay. All right. Enough fun. You all look riveted. Okay. All right. So we'll post a new version of the code online. We'll post this version and an updated version. I think there's some small issue I didn't catch before. But with that, that's model predictive control. That's how you apply it. Okay. Now, what I'll use the rest of this class is to talk about one of the key assumptions of model predictive control, which is it has what kind of dynamics? Linear. And Kevin Best answered in the past, linear. Okay. Now, that does not mean you're hopeless if you have a nonlinear system. Okay. And there are particular ways that you can use MPC on a nonlinear system in a really effective manner. Whoa, we just lose the projector. Okay. All right. Let me just, I will share my screen now. Okay. Last 5 minutes here. Okay. MPC with nonlinear dynamics. Okay. Now, there's lots of ways people can approach this. There are things called NMPC, which is nonlinear MPC, where you solve a nonlinear trajectory optimization problem. So one approach is just, we'll just run a trajectory optimization. I don't care if it's a QP or not. Maybe it'll solve fast enough. Okay, so one approach. So approach using an NLP. Okay, so you solve an NLP quickly. All right. It's a bit of an art form to that. There's literature on how to set up a nonlinear program so it's reasonably reliable to solve. It's a whole field. I won't go into too much detail here, but there are different approaches. But you probably don't have those same beautiful guarantees of convergence that a QP is going to give you. Okay, so it's a bit riskier. Okay, it's like, so solve an NLP quickly. Hopefully it solves fast enough and reliably in real time. And it's not crazy. People have done this, okay? And I believe PANOC is a drone, is an approach where people have for drones. They've set up a nonlinear program that's solved really quickly. That's really good, and specifically for like drones and avoidance. Okay, as a nonlinear approach, as a nonlinear programming approach. And it also depends on how fast you need to solve it. A colleague of mine in Legged Robotics, name was Ayunga Hared. He set up a co-location scheme that would run a trajectory optimization for a walking robot about once a second, pretty reliably. That wasn't fast enough to come up with control inputs, but it was fast enough where if you said, hey, DJ, I need you to walk at 2 meters a second now instead of 1, it only takes a second to think, and you're like, oh, okay, thank you very much. I can do that now. It only took me 1 second to do. All right. Number 2 is to linearize the dynamics. Okay. Now, that seems kind of obvious when I say it that way. You know, we talk about linearization all the time in physics and control theory and whatever, or system dynamics, right? Okay, where you would say that, oh, x dot is approximately equal to the partial derivative. Sorry, you guys use Q. Apologies. Q dot is equal to the partial derivative of your system dynamics, which we call H in this class, partial Q, evaluated at some, sorry, it's a Q, at some Q star and U star, okay, which is an operating point times Q minus Q star, where this is your A matrix, because that partial derivative, that's a Jacobian. Okay. That Jacobian will yield a matrix, and that's your A matrix. Plus partial H, partial U, evaluated at Q star and U star, U minus U star, okay? Plus H of Q star and U star. Okay. Now, some folks who take different kinds of control systems and control theory or linear systems theory, they'll say, oh, and by the way, this is your B matrix, apologies, your B matrix. Okay. A lot of them will say, hey, make sure that your operating point is what we call a fixed point, meaning that all your derivatives are 0. Okay. When you're linearizing, let's say it's a pendulum under gravity, linearize about this point or this point, because at those points, it's not moving and there's no accelerations. So why is that? That's because this term goes to 0. Okay. And at which point you have this beautiful AQ plus BU equation that we know and love so well. Okay. However, for MPC, you don't need to worry about that kind of thing. It's okay if that's not equal to 0. This is just in your defect constraints as just a constant. Okay. That makes it very, and there's a natural way that you can, it naturally fits into your defect constraints well. So that means you can linearize about not just these fixed points like the pendulum up, pendulum down effectively. You can linearize about basically any point. Okay. Please make it differentiable if that's okay. I don't like cusps. Okay. All right. As long as it's differentiable. Right. So I'll call this last term, I'll call it capital F. Okay. In MPC, and we're almost done, I apologize. We can set up our defect constraints using the dynamics Q dot is equal to AQ plus BU plus F. And thus linearizing about non-fixed points. Okay. I know we're like 2 minutes over, 1 minute over. The implications of this are cool. Okay. Not because what operating point should we use? Okay. You might say, well, wherever my system is at right now, we're sampling our state, right? Oh, I know where I'm at. I'll linearize about this point. A perfectly fine idea. Okay. Linearize about that point. MPC will then do a trajectory optimization and then move and then have a prediction for where it's going to go through the state space, right? Where it's going to go. All these points along the way. Well, for the next iteration of MPC, where should you linearize about? Well, wherever you are now. But also, you had a prediction as to where you're going to be. You can linearize about different points along the trajectory based upon your last solution. Okay. So it's a really powerful way. We call this MPC can succeed by linearizing along the trajectory. Okay, and that's it. That's where I'll end it for today. Okay, next class will be virtual. All right. And you all have a good day. Thank you all. Thanks, Michigan folks.